Your body has its own private, high-speed internet. It's an incredible network of lightning-fast reactions that keep you safe every single second of the day, and the amazing part is, you don't even have to think about it. Today, we're going to plug in and explore that incredible network, your nervous system.
Really think about it. That jolt of adrenaline when you're scared, or that split-second reaction when you touch something hot, you don't decide to do that. Your body just does it. It's all thanks to this brilliant, hardwired system that's designed for one thing and one thing only: survival. So what's actually happening under the hood?
Well, it all starts with what we call your body's emergency mode. This is the system that completely takes over in moments of danger or high stress. Its job is to prepare you to either confront a threat head-on or, well, get out of there as fast as you can. You can think of it as slamming the gas pedal to the floor on your internal engine.
See, your automatic nervous system really has two main settings, two speeds. You've got the sympathetic system, that's your fight or flight response. It's the gas pedal for high alert, emergency situations. And then you've got its opposite, the parasympathetic system. That's the brake pedal. Its job is rest and digest, bringing everything back down to a calm, peaceful state.
So let's paint a picture. Imagine a threat appears right in front of you. You don't have time to weigh your options or make a detailed plan. Your body just reacts. Instantly, it starts making a whole series of changes to give you the absolute best chance of survival. So what does this actually look like? First, your senses go into overdrive. Your pupils get huge to let in as much light as possible. Your eyelids pull back to give you a wider field of view. And anything that's not essential, it gets shut down. Crying isn't going to help you in a fight, so tear production just stops. And most importantly, your airways expand, letting you pull in a massive rush of oxygen to fuel what's coming next. Next, your body starts rerouting power. Your heart begins to pound, just hammering away to pump all that oxygen-rich blood to your muscles. And your stomach? It gets the shutdown command. Seriously, digesting lunch is the absolute last thing your body cares about right now. All energy is diverted away from it, and internal sphincters clamp down to lock everything in place.
Think of it like a battlefield triage for your body's functions. The walls of your bladder and rectum actually relax, but the sphincters that control the exits tighten up. The last thing you need in an emergency is a distracting bathroom break, right? So every single non-essential bodily function is put on an indefinite hold.
Okay, so the threat is gone. The emergency is over. You survived. What happens now? Well, it's time for that other system, the brake pedal, to take the wheel and bring you back down from that high alert state. And this part is just as critical for your health as the emergency response itself.
This is your body's all-clear signal. The parasympathetic system kicks in and does the exact opposite of everything the sympathetic system just did. Your heart rate slows, your breathing goes back to normal, digestion starts back up, everything chills out. It's not just about relaxing. This is when your body heals, grows, and stores energy for the future. It's actually why things like deep breathing or meditation work. You're consciously activating this brake pedal to tell your body it's safe.
But all of this brings up a huge question. How can these reactions be so incredibly, blindingly fast? How do you pull your hand from a hot stove before your brain even has time to register the pain? The secret lies in a very special kind of neural shortcut.
It's called the reflex arc. And honestly, the best way to think of it is as a hardwired emergency stop button. It's a shortcut. It doesn't need to send the message all the way up the chain of command to the brain, wait for the brain to make a decision, and then send a command back down. It's a local circuit that triggers an immediate automatic response.
Let's walk through that classic hot stove example. Step 1. Your skin touches something dangerously hot. 2. A sensory nerve fires a signal, but it doesn't go to the brain, it goes straight to the spinal cord. 3. And here's the magic trick. The spinal cord itself acts as a local command center. No brain required for this part. 4. It immediately sends an order back out through a motor nerve. And 5. That nerve tells your bicep to contract, and your hand is yanked to safety, all in a tiny fraction of a second.
So we've looked at the big systems and the reflex shortcuts. But what is the signal itself? What is this message that's racing down our nerve fibers at hundreds of miles an hour? Well, at its core, it's a pulse of pure electricity. This electrical pulse has a name. It's called an action potential. And that falling dominoes analogy, it's absolutely perfect. One domino falls, and it triggers the next, which triggers the next, in a super fast, unstoppable chain reaction that travels the entire length of the nerve. This is the fundamental language of your entire nervous system.
So how does that first domino get tipped over? Well, a nerve cell that's just waiting for a signal is like a coiled spring. It's not neutral, it's actively holding a slightly negative electrical charge inside, right around minus 70 millivolts. This is its resting state, primed and ready to go. Now, when a stimulus shows up, like the heat from that stove, it starts to push that negative charge in a positive direction. If it pushes it just enough to reach a critical tipping point, around minus 55 millivolts, well, that's the threshold. That's the point of no return. The domino is officially falling. And the second that threshold is hit, all hell breaks loose in the cell. Tiny little gates or channels that are designed for sodium ions just fly open. A flood of positively charged sodium rushes into the cell, causing the internal charge to skyrocket from negative all the way up to about plus 35 millivolts. That is the action potential. The nerve has fired.
But of course, a nerve can't stay fired forever. It needs to reset, and it needs to do it fast. So immediately after firing, those sodium channels slam shut. At the exact same time, a different set of channels, for potassium, open up. Now, positively charged potassium ions rush out of the cell, which brings the charge back down to negative. The domino is being set back up, ready for the very next signal.
Okay, so we've got this awesome electrical wave shooting down a single nerve cell. But what happens when it gets to the end? Because here's the thing. Nerve cells don't actually touch each other. There's a tiny, tiny gap between them. So how does the signal get across? That microscopic gap is called the synapse. And it creates a huge problem for our electrical signal because electricity can't just jump across empty space. To pass the message along, the signal has to completely transform. It has to go from being electrical to being chemical. Here's how that works. When the electrical signal hits the end of one neuron, it triggers the release of these little chemical messengers called neurotransmitters. These chemicals float across that tiny gap and latch onto the next neuron. And they basically carry one of two very simple messages. Some are go signals, telling the next neuron to fire its own action potential, and others are stop signals, telling it not to fire. And it's this constant, delicate balance of goes and stops that allows for all the complex processing in your brain. So, wow. We've gone from the whole body's fight-or-flight response all the way down to the level of individual ions crossing a cell membrane. Let's zoom back out one more time. What can we actually learn by listening to all of this constant electrical chatter in our bodies?
Well, we can actually listen in with a tool called an EEG. It's basically a device that measures the combined electrical activity of billions of those action potentials firing in your brain. And we've learned that the pattern of this activity, these brain waves, changes depending on your mental state. Fast beta waves mean you're awake and focused. Slower alpha waves show up when you're relaxed. And the even slower theta and delta waves appear as you fall into a deep sleep. It's a direct window into your brain's electrical symphony.
And that really brings us to our final, kind of mind-blowing thought. That simple automatic reflex of pulling your hand from a hot stove involves a cascade of billions of these signals. So just take a second and try to imagine the sheer scale of the trillions of signals firing in your brain right now, just to allow you to watch this, to listen, to understand, and to think about it. It is, without a doubt, the most complex and beautiful network we know of.